Good morning, everybody. How's everybody doing? Okay. It's day 3 for me, but a lot more for you. I guess you're probably hanging in there. Any questions, pressing things from last time? Today I don't have such a full lecture, so we have time. We can go slow. Okay, good. So maybe, actually, since we have a little extra time, let me review just a little bit of what we did last time, because I think we're going to use it heavily today, and I think there was a lot of sort of non-trivial formalism. So just a couple of key equations. We were talking about field space geometry, right? And the key idea was that we write the Lagrangian with a half for convenience, Gij of phi, d mu phi I, d mu phi j, and we identified that this object here could be interpreted as a metric on field space so it defines a notion of distance on field space for us. We can use it to construct objects that transform covariantly or objects that are invariant under field redefinitions, right? In particular, field redefinitions without derivatives. So we had this class of field redefinitions. Phi goes to phi tilde of phi, right? And under this, for example, Gij transforms as a tensor, and we could construct objects like the Ricci scalar, which is an invariant under field redefinitions of this type, okay? And we had lots of great questions about generalizations of this, what happens when you include either higher derivatives or field redefinitions with derivatives, which are also supposed to leave the S matrix invariant. And the answer is that while this is a very powerful formalism and we're going to put it to work for us, I hope you'll think in an interesting way, to ask this question whether or not SMEFT exists at the O4 fixed point, but it is limited, okay? And as you've been learning since the beginning of this school, EFT is all about doing a systematic expansion order by order in operators, which of course include higher derivatives. And as we talked about, 2 lectures ago now, right? This idea that S matrix elements are invariant under field redefinitions covers a much broader class than just this set. Nonetheless, we have this necessary condition for invariance, okay, which is that we should be building our observables, namely our amplitudes here, so they're pseudo-observables, in terms of objects that are such as the Ricci scalar, okay? And like I mentioned last time in my notes, there's a few examples of how to actually construct S matrix elements in this language directly by writing down Feynman rules in a geometric way and then computing amplitudes using just standard Feynman diagram techniques. And what you find are objects that are manifestly written in terms of invariance in field space. Okay. By the way, let me say just 2 more words about that. In case you're interested in this and you go look at some of my papers or some of the related papers that I was mentioning, often what we do is we actually write the amplitudes where we strip off the LSZ factors associated with the external legs, so that what we have is an amplitude with open indices, one for each of those external legs, so that on the right-hand side we have something that transforms covariantly. Because if you just have something invariant, it's a little hard to diagnose, and so we actually find it more convenient to write the amplitude in this kind of stripped way, okay, an amputated amplitude, because then it transforms covariantly, okay, and you can really see that the open indices on the left-hand side, which correspond to the legs in the amplitude, have to correspond to open indices on the right-hand side for the geometric quantities that appear in the amplitude, okay? So if you look at my paper I was talking about, this unitary violation paper, you'll see all of our expressions look like that, okay? And actually in the papers from Helseth and collaborators, they actually recognize that you can identify these wave function factors with Vierbines, okay, if you're familiar with that term. So there's even a geometric interpretation there. Okay, so there's some very nice stuff out there just in terms of field space geometry and understanding amplitudes in this language. Yeah, there's one other thing I thought to say and now I forgot. Maybe it'll come back to me. Okay. Good. I also mentioned last time this trick of going to normal coordinates, okay, which again computationally is extremely useful. Oh, good. That's what I was going to say. Another property of these amplitudes. Let me just give you one example. See, and now I'm going to run out of time because I'm blathering on. But just to give you one example of this. Okay, this is an aside, but I think it's important because it's kind of, at some level, it's the whole point, is that the objects that are invariant are the amplitudes, right? And we can write them this way. But for example, if we do, the claim is if we do pi pi to pi pi scattering, just for example, I won't draw the diagrams, but the matrix element goes something like S times this kappa phi evaluated at the physical vacuum. Okay, and the last little point I want to make in this aside is just that with field space geometry, with amplitudes written in terms of field space geometry, what you'll always find is kinematics, so this is the Mandelstam S, okay, times some field space dependent quantity. So another way to think about sort of what the field space geometry is doing for you in terms of amplitudes is it sort of factorizes kinematics from field dependence, okay? So all of the kinematic factors are multiplied by these universal field dependent factors where you can compute in this general language once and for all some amplitude, right? Remember, this is this sectional curvature. I put phi here, I should put pi. Okay, and I defined this last time at the end, okay? So you can write everything in terms of this object that's manifestly invariant. This is an invariant amplitude, right? S is Lorentz invariant, kappa is field space invariant, right? If I do one of these field redefinitions, then kappa doesn't change. And, but this is kind of a key aspect when you look at these formulas. You'll see the more complicated ones, they all have this form. One of the tricky things when you start incorporating, so you know, I think it's very interesting. It's a big open question. Nobody knows what to do with how to generalize all of this. Okay, maybe one of you will discover the right way to think about that. But the point is that as soon as you go beyond what we're talking about here in terms of field space geometry, now you end up mixing, a transformation can mix kinematics and field space, okay? Because if you start including derivatives in your field redefinition, derivatives are, you know, essentially change the kinematic dependence. And so one of the things that breaks, just from a very practical point of view, is this factorized form, okay? So again, those of us who have thought about this for a while, we really don't know what to do because everything kind of relies on the simplicity that comes from studying the theory at two derivatives and so on. And I should say, I mean, there are, again, my friends, Chung and Helseth and Par Martinez and their collaborators, they have some proposals for how to kind of take field space geometry and kind of jam some extra stuff in so that they can extend it to include some extra terms. So if you read their geometry kinematics duality paper, there's some games that they play there that can take these formulas and apply them to a wider class of theories, but it's a bit tricky, okay? I think it's very cool, it's very clever, but it doesn't really solve the problem, okay? And I think they would agree with that. Yes? Yeah. This is tree level at just the 2-to-2 scattering, absolutely, yeah. So my expectation is yes, but actually there's no calculation sort of in this modern hefty kind of literature that I know of that go to one. Indeed. Yeah, so absolutely. So
I was just wondering whether the derivative level field definition are actually encoding some sort of a loop.
I think it's a different thing. I think it's more like those are changing the structure of higher dimension operators. So it's even going to be an issue at tree level. But absolutely, so to my knowledge at least, the state of the art for loop corrections is this work by Manohar and Helseth and others looking at RG. So the RG already they show the RG similarly has this kind of factorized form, which is very interesting. And I think everybody expects that there's a way to understand loop corrections, one loop amplitudes or even higher, again, in this sense, but it hasn't been explored so much to my knowledge. And there's a tricky thing with loops, of course, which is picking a scheme. And so, yeah, so there's a lot of kind of technical questions. And I think well, for me at least, the motivation to do that hasn't been so clear. Anyway, let me just leave it there. I think that's a part of why, with a lot of this stuff, it's really only been explored at tree level so far. But yeah, but again, for those of you thinking about things you're interested in, I think it's definitely if you can find a good question that requires you to think about this at loop level. It's hard, but it may be worth pursuing if you get excited about this stuff. Okay, good. So now I think I prefer to be pushed for time. Kind of gets my adrenaline going. So now I've taken almost 15 minutes. So we'll fill the rest with new stuff. So let's, unless there are any questions, I'm happy to keep chatting. Okay, good. So let's get back to the central question of today's lecture. Does SMEFT exist? Okay. And I'm a broken record at this point, right? We want to ask this question in a way that eliminates this ambiguity due to field redefinitions. Remember now, a few lectures ago, maybe I forget which day. It's all blurring together at this point, but a few lectures ago, right, I did this kind of strange thing where I took the free theory and I did a field redefinition on little h, and I showed you in terms of big H that the Lagrangian looked like a mess and was not obviously analytic and a good EFT, okay? So I set the stage. Hopefully now you're very motivated to understand why we would want to use this language in order to ask these questions, okay? So we already have one condition we talked about last time. Which is, we need this to be able to find the existence of this so-called O4 invariant fixed point right? And Alonso, Jenkins, and Manohar have this beautiful derivation of this where they make an argument that you can identify this in the HEFT Lagrangian by solving for the coefficient of the Goldstone term equals 0, and that identifies this, this O4 invariant fixed point that we call H star, and we identify as minus the VAV, right? So this tells us how much do we need to shift little h in field space in order to find what could be the point in field space where SMEFT would exist. And in particular, when we say, talking about this, just to remind you from yesterday, saying that SMEFT exists is really saying that if we can reach that O4 invariant fixed point on the manifold, then we should be able to take our polar coordinates and rewrite them as Cartesian coordinates, okay? So that's as far as we've gotten. Now we want to do more. So this is all based on this paper, Is SMEFT Enough? By myself, Nathaniel Craig, Xiaochuan Liu, Dave Sutherland. It's a long paper, and I'm just going to tell you the logic of the argument we give in that paper, because then there's a very tedious proof that we buried in an appendix. If you care, it's there. It's quite detailed. It uses it's a recursive proof. Okay, it's 5 pages of algebra basically, just showing that this holds. But what I want to explain is the logic. Okay. There may be a more clever argument, but I think this one is at least robust, okay? So let's present the logic of an argument. And maybe let me emphasize when I say SMEFT exists, right? Again, we already have this condition. The O4 invariant fixed point we need to be able to access the O4 invariant fixed point on the manifold. But what else could go wrong is that when we go and we try to write linear coordinates, we get something non-analytic. And then we don't, it's not SMEFT. We don't know what to do with a non-analytic EFT. And so what we're looking for basically is extra conditions that need to be satisfied in order that the EFT is an analytic expansion in fields and in principle and derivatives, but that's not really being explicitly covered here, okay? So that's what we're looking for. So here we go. The first step of our proof is we write the most general SMEFT Lagrangian, of course, up to 2 derivatives. Step 2 is we canonically normalize the kinetic term for H. I guess maybe I should have said then we go to the physical vacuum. Okay, so we take the SMEFT Lagrangian and we plug in that map that I presented, I think, on day 1, right, which takes us to the physical vacuum. This is what we always just do with the standard model. Okay, so we write things in terms of, so our variables are h and pi, or n, okay? Then, in step 2, we canonically normalize the kinetic term for little h, okay? And I won't have time to show you, it's a couple of pages argument in the paper, but the claim is that in this 2-derivative version of HEFT, when we canonically normalize the H kinetic term, that fixes the field basis for us entirely, okay? So this fixes the field basis. Okay, that's important because we want to make an argument that's unambiguous, okay? So the idea, should be an A. The idea is is that if we can make an argument in one basis, then perhaps we can covariantize that, okay? And write whatever we learn in in terms of geometry, in geometric quantities, which makes it manifestly field redefinition invariant. Okay, so that's the idea, and then step 3 is to do exactly that. 3 is to rephrase the basis specific criterion in terms of curvature invariance. So that gives us a basis independent criterion. Okay, so it's really, it's so simple, it's almost trivial, but actually showing it is a mess, as usual, right, with these things. But I hope that the logic is hopefully compelling to you, right? It's really, once I have some criterion in a fixed basis, if I can take that, whatever lessons I learn, write them in a way that's sort of geometric, that's written in terms of invariance, then I'm done. Okay. In higher dimension. Oh, absolutely. Yeah. It's indeed. It is because we have this arbitrary function of the fields, right, in front of each of these terms. A function of, sorry? Yes. Exactly. Yeah. Yes. But indeed, one of the key things about doing EFT is we need to truncate. Yes. Exactly. Yes. Yeah. And of course, in when we write this, you might, well, you can like it or not. This is what we did in HEFT. Depending on power counting, etc., you may actually order the particular order in power counting you're working. You may have some of these terms with higher order in the fields. In SMEFT, of course, because mass dimension is coupled to the derivatives carry mass dimension 2, really to do something that is systematic in power counting, you of course would need to go to higher derivatives, okay? So what we're really giving here is a necessary condition for SMEFT to exist. I wouldn't at all be surprised if you told me that you went home and in 5 minutes you constructed an example with a 4 derivative term that broke this, right? So this is not a necessary and sufficient condition because it's only going to 2 derivative order. Nonetheless, as you'll see next time when we interpret this criteria, it gives us, I think, a lot of insight into the types of theories that live in that wedge outside of SMEFT, but still within it. Well, so certainly this is going to be true in any basis, okay? If you go look at what we had to do to prove this, I wouldn't know necessarily how to generalize it, right? So there's actually, one of the main technical results in this long paper is there's sort of 2 aspects. One is showing that this is true, which we do very carefully, okay? because it's not totally obvious. Kind of intuitive, but it's not totally obvious. And then the other thing is that this, like I said, this is actually, this is really due to Xiaochuan Liu. I mean, this took quite a bit of effort to really show rigorously. Okay, we proved it by induction, and it's a mess. Okay, so I just want to give you, you know, I mean, a little bit more than just this strategy. And then I'll tell you what the criteria are, and then that'll probably be it for today. Next time we will talk about applying that to an example, and then I'll tell you a little bit about what else is in the paper. You can go look. So so let's unpack each of these in order. One, we want to notice that when we map from SMEFT to HEFT, so we write the Lagrangian SMEFT is A of H squared plus 1/2 B of D H squared minus V tilde, and that equals 1/2 A plus V plus little h squared B D H squared plus 1/2 V plus H squared A times D and vector squared. Okay, I'm just not writing the arguments, but these are, of course, functions of capital H. And, actually in this language, these are functions of little h, and then minus v. And then that lets us identify this k function that's the one we write in HEFT in terms of the SMEFT function. So we have a plus v plus little h squared v, and we have vf is v plus h square root a. And again, this is very similar in spirit to showing you that map going the other way, but just notice, right, we have square roots, and so immediately you should worry about potential analyticity problems, okay? So here we are assuming that we have SMEFT, so that tells us that A, B, and V tilde are analytic functions. And we have, I guess I should have written that over here. We have other conditions for A, B, and V. So if we know h squared is just v plus h squared over 2, we also know that A of 0 is 0, and is that what I mean? Sorry, this is wrong. I didn't. That's right. I didn't write the arguments. This should be dh squared, and then this. This should be 1. And v prime at little h equals 0 is 0, okay? The potential is minimized at the VEF. Okay? So that translates in terms of F, V, and K into the following. So this implies 1, f of h star equal, which is minus v, remember, equals 0, right? SMEFT is certainly going to have an O4 invariant fixed point. And v prime at h equals 0 is 0, okay? The Lagrangian in the physical basis is certainly going to be expanding around the minimum. And 2, k expanded around h star, f expanded around h star, and v expanded around h star are real analytic functions of little h. And then when we expand about h equals h star, what we find is k and v are even functions and f is odd in h minus h star, which is equal to v plus h. Okay, and we also have a of 0 equals 1 translates to k of h star equals v f prime of h star equals 1. Okay? So that's at h equals 0. Right? That's just saying that the first derivative of the potential at the minimum is 0. Right? Because that's little h. That's like saying big H equals V. When we do, right, H minus H star takes us back to the origin where electroweak symmetry is restored. Okay. And this even and odd property, so for the potential, it should be pretty obvious because the SMEFT potential is a polynomial in gauge invariant, or in this case, global symmetry invariant quantities, magnitude of h squared. So that's all I'm saying here, okay, is that when I say v is an even function in little v plus h, I'm just saying that if I have SMEFT, then I'm only writing magnitude of capital H squared, right? Magnitude of capital H to the fourth and so on. And that translates directly into just an even function of v plus h. Okay, for the other two, you need to use this translation, but basically it's the same idea, right? A and B are analytic functions of capital H, which means they're functions of magnitude capital H squared, right? We can't have square root capital H squared. That wouldn't be analytic at the origin. And so that immediately tells us that we can expand these square roots. Here we're just going to get an even function when we expand the square root. Here, because we have this extra factor of v plus h, we're going to get an odd function. Okay? So again, the recursive proof is a mess, but otherwise the logic is hopefully, well, we have the time. I want to make sure everybody gets it, okay? So we're saying, so you know, this isn't such a physical condition per se. I mean, it's really encoding the fact that there's an O4 global symmetry, but so I guess that's the physical way of saying what this sort of even and odd condition is, but it's really just a simple property of the map. Okay. Yes. No, that's trivial. There's absolutely no obstruction, because if I have SMEFT, HEFT is just expanding SMEFT in the physical vacuum. Okay? That is full stop. no question that you can always do that. Okay? That's not the question. The question is, if I start with the Lagrangian written in the physical vacuum where I have heft, can I go back? That's the hard question. And it's not always true that you can go back to SMEFT. Okay? Going from SMEFT to HEFT is trivial. Going from HEFT to SMEFT requires you to satisfy the conditions that we're working out. Okay. But in order to show you what is required to make that map, right, I'm going to start with SMEFT. I'm going to go to HEFT, realize that it has certain properties, and then try to encode those in a field redefinition invariant way. Thanks for the question. Yeah, I want to make sure that it's really clear what we're doing here, because this is all we're talking about today, basically. Yes. But it also, yeah, but it's field dependent, right? So it also has this, but yes. Yeah, exactly. Okay, great. Okay. So, I mean, at some level you would say, well, this is it. It's pretty easy. You have, now you know how to look at a Lagrangian written in terms of little h. If you can organize it as if you can combine v plus h and then look, are the terms even, odd? Does an O4 invariant fixed point exist? Done, right? But of course, the problem is that this even and odd statement is not field redefinition invariant, right? Obviously, if I send h goes to h plus h squared, right, I'm going to completely destroy any notion of even or oddness, right? I take an even function, I replace h in that function by h plus h squared, I'm going to get even and odd terms, right? Okay, so this is, at face value, very specific to a special basis, right? So again, if I start with SMEFT and it's analytic and I write it in the physical vacuum, I'm going to see this, okay? But if I want to start with HEFT in some random basis, then I am no way guaranteed that I'm going to have this even and odd properties, right? So that's really the problem. This whole thing is not field redefinition invariant. Okay. So next I want to explain a little bit more about how we're going to make sure that we're fully fixing the HEFT basis, right? Because again, in the logic, if we can find a criteria in a fixed basis and then we can geometrize it, covariantize it, then we're good. So I just want to say a few words about a little bit more technical detail about what it takes to fix the basis, at least the choice we made, okay? A natural choice is to canonically normalize the little h kinetic term okay, so we let v1 plus h1 equal some function q of v plus h. which is given by the integral from 0 to v plus h dt k of t, where t is just some integration variable. And what this gives us, the reason this is useful, this way of writing the field redefinition that we're going to use to fix the basis, is then we have the relation dh1 equals k dh2. Probably mean this. There's no h2. Yeah, that looks right. So that, right, all I'm doing is taking the derivative of this formula, and so, right, this is going to relate the kinetic term, because remember the kinetic term had k squared. I guess it's not written here. But if you look back, right, just the convention that we're using, the kinetic term was given by h squared. Okay? So this is the way we're going to fix the kinetic term of little h. And again, I'm going to claim, without going through the details here, it's just checking cases. What about kinetic mixing? What about this case? What about that case? Does the field redefinition exist? I think it's, you know, it's all just kind of straightforward checks of all the things that you might worry about are unfixed by this field redefinition. It turns out that this is enough for this two-derivative theory. So we claim this fully fixes the freedom to redefine H and N vector. And the arguments given in section 4.1.2 of is SMEFT enough? It's not enlightening, or I would have taken the time to present it. And then we get HEFT is just, and notice, of course, this is going to change the definition of F, right? The coefficient of the Goldstones. So now there's no field dependence in front of dh squared, right? And this is really, you know, it's not just fixing, by the way, we're not just saying that that this has canonical normalization. We're saying there's no field dependent coefficient, okay? So we're what this transformation does, right? It redefines this field, little h, into h1, so that we've absorbed all of the field dependent stuff into the other coefficient. Let me write it. And into the potential, of course, right? So here I've relabeled h1 back to h, right? I don't want to call it h1 over and over. And I've redefined these functions, right? I've done that transformation, now I have a new Lagrangian. Okay, and I dropped all the little subscript ones, okay? Don't let that confuse you. So I have a new potential, I have a new f, and I have no field dependence here. That's exactly right, yeah. That's the point of doing this, is to remove all the field dependent coefficient here, okay? And that's a big field, I mean, that's, you know, it's non-trivial. So, and maybe it's to give you a little bit of intuition here, right? It's really that n only appears at this two derivative level as dn squared. And so all of the kind of non-trivial interaction stuff is in little h. So it's not so surprising that if I, right, it's a big field read, you know, I'm picking order by order, right, this field redefinition. And so it's maybe not so surprising that that I'm moving all of the interactions from here into here and here. Indeed, indeed. Yeah, like I said, I dropped here. I dropped all the little subscript ones, the primes or whatever you want to call them, right, from the redefinition. Yeah. So this is in a very different basis than the original basis, than the one I wrote here. Notice, right? Look at what I mean. This k function is what would have appeared in front of the derivative of little h, right? That's in principle, very complicated, right? So this is the thing I'm absorbing into a new definition of f and v. I didn't write it here, but again, the claim, this one maybe I should have written up a little bit, but I'm just going to claim that so there's two things about doing this field redefinition that are helpful. One is that it simplifies the Lagrangian a lot. The other is that it maintains this even and oddness. Because if you like, I have some even function, I multiply it by an even function, I get an even function. I have some odd function, I multiply it by even, I get odd. Okay? So this maintains the even/odd properties of f and v. Okay, so that's kind of critical to the argument. Okay, and then step 3. So I geometrize the basis dependent statements So in order to do this, notice, right, here I have some arbitrarily high polynomial function, okay? Here it's odd, I have some arbitrarily high even polynomial function. So I'm going to need to map effectively an infinite number of conditions to an infinite number of conditions. Of course, as I've said many, many times, when doing EFT, we should truncate these things. Nonetheless, right, I should have something that works to arbitrary order, okay? And as you'll see tomorrow, actually to apply this criterion, we're going to need to do matching calculations to all orders in the fields, okay? So let me just tell you what this map is. Again, this is the thing we prove in this long appendix. So we have the term f to the 2k, so this is just the 2kth polynomial term in f, at the origin in field space, h star, right, the fixed point, equals 0 for all k in n. So this is saying f is odd because all the even components of f are 0. We have put the prime in the wrong place. Vf prime of h star equals 1. And we have v to the 2k plus 1 at h star equals 0 for all k in n, the natural numbers, right? That's just saying v is even, okay? So, right, these are the even and oddness conditions. This one, it's still over here, is this condition that we started with a canonical kinetic term for capital H, and that translated into a condition on the kinetic terms for little h and n, okay? So these three conditions together can be translated into the following. So we want f of h star equals 0, right? That's telling us the existence of a fixed point. Again, these are sort of the Lagrangian level statements. These are the geometric statements, right? So here I want to talk about, I only am allowed to ask questions of my field space manifold, right? In other words, if I were doing the argument in this style, I would be analyzing the properties of a Lagrangian in this specific basis. But over here, all I know are properties of the field space manifold, okay? So there's these two infinite, right, conditions. I need every term up to arbitrary order to be even or odd. And it turns out that corresponds to taking covariant derivatives in field space of the Ricci scalar evaluated at H star to be finite for all n in n. And similarly for the potential, so this is effectively the condition on F, okay? And then for the potential, again, we need the potential and all of its covariant derivatives to be finite, okay? And again, this map is proved in Appendix B. Okay, so this is technically correct, but only so useful because it's asking for an infinite set of conditions. But of course, you know, it's nice to have a set of criteria for determining whether or not this map from SMEFT to HEFT exists and is analytic, et cetera. But we want something we can use, okay? And so we conjecture and then we show through example that most theories we're interested in are probably going to satisfy, I would say this motivates a leading order criteria for the existence of SMEFT A, f of h has a 0 at some point h star. B, k, f, and v have convergent Taylor expansions C, the scalar curvature R is finite at H star. Okay? So at least in order to explore, because again, what at least my interest is here is ultimately, I don't care so much beyond knowing that a criterion exists, like the technical details of the criteria are only so useful to me. What I care about is ultimately, I want some way to understand what theories live in this space where I can have a perfectly well-defined heft, but I can't rewrite it as SMEFT. I can't go to the origin of field space and write something in terms of capital H in these linear coordinates that we like to use when building models. And so this leading order criterion gives me a very straightforward set of conditions that I can apply. Now, if you hand me your heft Lagrangian, I have a very well-defined crank here. I just turn. Okay, first I look for the O4 invariant fixed point. If it's not there, then clearly I can't rewrite my polar coordinates and linear coordinates, right? Because AJM told me I have to be able to go to this O4 invariant fixed point to find the sort of capital H, the Cartesian coordinates in terms of capital H. I need K, F, and V to have convergent Taylor expansions for them to be anything like an EFT, okay? So I need to have some polynomial in fields and in principal derivatives. Of course, that's outside the scope, but that's the idea. And then here, this kind of the fun new thing that relies on field space geometry, which is that I want to test that at the fixed point, the curvature is finite, okay? Again, very intuitive. You would expect a physical theory, right? It's not going to have a singularity. So it's not at all obvious. That's in this map. Yeah, so I don't have good intuition for, we just figured out a way to map this sort of even and oddness onto the fact that basically, I mean, all I can tell you is here I have an infinite set of conditions, and the claim is that that maps onto this infinite set of conditions, okay? But actually, I mean, yeah, maybe it would have been helpful to do some lowest order thing, but I'm already out of time, but as I was worried about. So you can look in the appendix, you'll see, you get a flavor very quickly for the proof. I mean, it's very brute force, okay? It's not like we have some clever, slick argument. We just really by induction, we prove the first step, then we prove the nth, assume the nth step and prove the n plus one, right, of that mapping. Good, so, well, I have 1 minute, but I'm basically out of time. I just want to, because this is maybe a little bit dry today, next time I hope you'll, we'll bring this all together and talk about physics, okay, the consequences of this. And I hope you'll find that really interesting. But I want to maybe, since it's been dry, I want to just inject a little bit of fun, which is to say that for a long time, I was advocating that we call this paper "Heft is a black hole," because very loosely, okay, I know black holes don't have physical singularities at the horizon, et cetera, but just very loosely, you can kind of think of this as a condition for no horizon, right? In the sense that I can get access to the origin in field space, right? If this point doesn't exist, as has come up a few times, and I'll definitely emphasize next time, this is basically saying that there are extra sources of electroweak symmetry breaking, okay? So something we do a lot in the paper is plot field space manifolds, and there's lots of pretty pictures there. We discussed this concept of the EFT submanifold, okay? So basically, if you have some full theory and you think about that in field space, then by constructing the EFT, you're kind of taking a slice, okay? And we make that concrete, although there are caveats, but you can see we have these beautiful plots of contours in field space. So we show examples when you have extra symmetry breaking, right? That means, that's what this is kind of telling you, is that just with little h, right, you try to get to the fixed point and you hit a wall, right? Because physically what's happening is there's some other degrees of freedom that need to come in to help you, that play a role in restoring electroweak symmetry, right? So the physical picture is that you can't access the origin in field space where electroweak symmetry is restored just with little h, okay? So we say that's kind of like having a horizon, right? And then this is kind of like a naked singularity. Okay, right? This is saying that even if you could get to the origin in field space, when you get there, the curvature explodes, right? And so it really has the flavor of black hole physics. And so I always think of this paper, and I usually have a slide when I was going around giving talks about this. HEFT is a black hole, where I would kind of emphasize the physics of this point. So that's the slogan I'll leave you with today. And for once, I'll end on time, maybe only 1 minute over, 2 minutes over, and happy to take questions. And then, like I said, next time, today was putting you to sleep. I hope next time I'll really make it up to you by driving home the physical point of all of this, and maybe motivating you also to want to learn about functional matching techniques, because we'll look at examples where we were able to derive matching formulas, like in the sense that Rodrigo was telling us about, using these techniques directly in the path integral that let us derive formulas that are all orders in the field, so we could actually apply these criteria to examples and really see physically what's going on. Okay, so that's what we'll do on our last day together tomorrow. Thanks as always for your attention, and happy to take questions and chat over coffee and everything. No, I mean it's so the probably okay. So yeah, and you're asking about more than two derivatives, which is, I think, a fair question, right? I want to distinguish that from doing field redefinitions with derivatives, okay? So if I just restrict myself to coordinate changes, to field redefinitions without derivatives, but I have higher derivative terms, I'm guessing that there's a, because there's almost certainly another line here you could write, because you probably would get some even or oddness properties, and but I worry. Okay, here are the things that I worry about. Here's why I don't just have an obvious answer, like it's like obviously it's just covariant derivatives of some, because for one thing, there are now multiple operators in principle. You can use integration by parts to change them. So there's probably some canonical choice I could make, right? Where I then could play this same kind of game. That would be my guess. And it'll be very similar, right? I mean, what you need, kind of, and again, intuitively it makes sense. It's that you want the manifold to be well behaved at the electroweak restoration point. So this is, by the way, I don't know that this is necessarily a unique test, right? Is it if? I don't know. I remember when we were doing this, now it's like 5 years ago. I remember when we were doing this that, we were making, we played with a lot of different things, and I think we ultimately, this is a very convenient choice, but you can imagine different contractions. So I would be careful. I think this is if and only if. I don't know that it's like, that there's not another way to organize this that would also work, right? So anyway, there's a lot of kind of detailed things, but I think the lessons are, I'm confident that the lessons will just carry over. I guess to me, one of the reasons that I think this, even, here when I simplify it and I write this leading order criterion, why do I think this is useful or compelling? It's going to be because then when we do matching examples, it tells us something useful. And so I think that, and again, this is why maybe this is really a good argument for why it's interesting to have worked with this two derivative theory even though we of course know it's not the generic EFT, is because it already is going to give us some physical insight. And then if you do matching, of course you're going to generate this full tower of operators. So maybe that, to me, the way I think about it is, I do a matching calculation. Yes, I generate a real EFT, not this weird subset of EFT. Nonetheless, I can look at the part of it that's obviously geometric, and there I can ask this question. And I think in any concrete example where you're integrating out particles, if it satisfies this leading order condition, it's going to satisfy whatever extended condition you come up with. I do think, I don't know that this is like a good use of anyone's time, but I also believe that you probably could violate this. You could tune some things in principle, right? You could have multi-particles in the UV with very specifically chosen coefficients so that you evade this criterion, but you'll never be able to evade this one, right? This one I think is rigorous. Not I think. This one I would, you know, I would bet, well, I never bet my life, but I'd bet, you know, a month's salary or something that this is rigorous. And mostly because I have awesome collaborators. I don't make mistakes. But no, we vetted this quite hard. And so, yeah, so I think this applies, you know, so you could evade, again, it might be a fun thing like as a master's project or something, right? To just try to evade the leading order criteria, see how horrible of a thing you have to do in the UV, right? Good. Let's go do that. All right, thanks everyone. I'll see you around and tomorrow.